Okay, we are going to estimate a population mean. And so our focus or our goal here is to estimate mu, which is our mean, our population mean, when the standard deviation is unknown. So we'll be using samples in order to estimate those. And you have a new chart, which is called the t-distribution chart. So if you look at this, some people also call it a student t-distribution. It's just a different chart to find the area or the probability. Something new here is called degrees of freedom. And degrees of freedom is found by taking your sample. DF is found by the sample size minus 1. So the chart can be useful for going all the way up to 40, and then it starts skipping around, and then it goes to 100, and then starts skipping around again. But if you're using the table, you can estimate your degrees of freedom. So let's say your degrees of freedom would be, if your sample size is 110, your degrees of freedom would be one less than that. That'd be 109. And so the closest one for our t-distribution chart, our degrees of freedom would be 100. So we would use that. We have our area in one tail if we're just looking at it this way. Or we can look at an area in two tails like this. And we're still using that alpha. We can do just the alpha, or we can do alpha over 2 to represent our two tails. All right, so we have a point estimate, x bar. That is going to be our sample mean. It's a single value estimate. We're still doing confidence intervals. We have our lower and our upper. Our lower is found by doing x bar minus e, which is our margin of error, which we found that in 7.1. Or we can do x bar plus e. Estimate of the true value of a population mean written as an interval. Our sample size, we should know how to find the sample size to estimate the population mean. So we'll be given a question that says, what sample size do we need if we want a confidence interval of this with a mean of this? And we'll be able to find what that sample size is. The sample mean x bar is the best point estimate of the population mean. And then we have these notations that we've been using for a little while now. This is our population standard deviation. So we do not know that in these problems. So it's pretty common that you won't know your population standard deviation. So we'll know our sample mean, our sample standard deviation, the sample size, and that will help us find our margin of error. So we are using the t-distribution chart. So we are going to do our margin of error is found by doing, instead of z, which was our z-score, we're going to do our t-distribution at alpha over 2 times our sample standard deviation over the square root of our sample size. The requirements to estimate the population mean is that the sample is a simple random sample, and either both of the condition, either one or both of the conditions are satisfied. Population is normally distributed, or our sample size is greater than 30. The format of our confidence interval, same as what we did in 7.1. We take our sample mean, we subtract our margin of error, and then we add it. So we can write mean plus or minus the margin of error. And then we have our margin of error. We are going to use degrees of freedom equals n minus 1 whenever we use our new chart. So I'm going to put that over here. Use chart A3, which is called T distribution. Our critical values will be found on our chart. So when we were doing 7.1, we were talking about the z-score, and we were doing z alpha over 2. Now we're doing t alpha over 2. Separates an area alpha over 2 in the right tail. Degrees of freedom. This tells us how many we could actually find, how many of the samples that we could actually use in order to estimate our population mean. So you take what's in your sample size and you subtract 1 from it. We have different confidence levels, 90%, 95, and 99. Those are the most used. And so we find our alpha by doing 1 minus our confidence level. And we did this yesterday. And then we could also do the alpha over 2 to find, if for this one, it would be 0.1 divided by 2, so it'd be 0.05. So this depends on if you want to look at it area in 1 tail or area in 2. This would be considered area in 2 tails. And this would be considered area in 1 tail. So let's look at our chart, and let's say we're doing degrees of freedom of 10. So let's say there are 11 samples. So degrees of freedom would be 10. Let's look at area in 2 tails at 0.1. So we'd look at 10. Then we'd look at area in 2 tails, 0.1, which is 1.812. Which is the same as saying, if I divide it by 2, alpha over 2 is 0.05. Area in 1 tail. See how they're the exact same number? So you can look at it either way, area in 2 tails or area in 1. You can just look at it as alpha. So let's say alpha is 9. Your confidence level is 90, then your alpha is 0.10. So you just look at alpha being your area in 2 tails, 1.812. This number will be used to find your margin of error. Okay, let's keep on rolling. Student T distribution. It's different for different sample sizes. So that's why we use our degrees of freedom. For the T distribution, the mean is T equals 0, just like standard normal distribution has Z equals 0. It has the same general symmetric bell shape as standard, but it has greater variability that's expected with small samples. If you have small samples, there's more variability in your outcome. As the sample size gets larger, the distribution gets closer to looking like a normal standard distribution. But with T distribution, again, we're dealing with a small sample. So we have this formula, which we're really not going to be using because we have our table, and we have calculator that we can use. So to find the T alpha over 2 can be found using technology or the new table. So let's go to our calculator just so we know where it's at. It's going to be T interval. So we'll go to stat, over to test, and then do T interval. And then these are our options that we can do. If we pick data, that means that we can use a set of raw data from our list right here. I put in some data in here. We can use raw data to do this T distribution, or we can go back to it, or we can use stats. We can plug in what we know. We know our sample mean, our sample standard deviation, N, which is our sample size, and then what confidence level we want to find. Okay, so that's how you use the calculator for it. Keep on going. Procedure for constructing a confidence interval. We're going to go through this real quick because we're actually going to do this on an example. So 1, check the requirements. 2, we are going to find the critical value, alpha over 2. After we find that, we can find our margin of error and then write our confidence interval. Rounding, use original data, round one more decimal place than the original data, or summary stats, you're going to round to the same number of decimal places as your sample mean. Okay, example 1. We're going to find our critical value, T alpha over 2, corresponding to 95% confidence level, given that our sample size is N equals 15. So the only thing we're asked to do is find the corresponding value. So we know a couple things. We know N equals 15, so we can find our degrees of freedom. You take 15, subtract 1 from it, so equals 14. And then our confidence level is 95.95. So the alpha is 1 minus 0.95. 0.05. So this would be considered in our two tails, area and two tails. Or if we do alpha over 2, we get 0.025. That would be called our area in one tail. So we'll just look at our chart. So we want to look at the degrees of freedom where we have 14. So there's 14. And then 0.05 for our area in two tails. So 0.05, come down, 2.145. That's our critical value. Okay, let's go to the next example, the one that I did on a separate sheet that's typed up. Look at this example. So it says, use the data below corresponding to the birth weights of baby girls measured in HG. Here's our summary stats. N equals 15. X bar, which is our sample mean, is 30.9. And then our sample standard deviation is 2.9. We want to construct a 95% confidence interval. So we actually have raw data, but we first need to check our requirements. So number one is it's a simple random sample. So yes. Then B was, is it normal or is N greater than 30? Our N equals 15, so it's not N is greater than 30. But there is a way to check and see if our data is normal. So everybody go to stat. And we want to put in our data in L1. Go ahead and do this so that we can check and see if this is a normal distribution. So there should be 15. Make sure you got 15 data points. Okay, do you remember the QQ plot? Do y'all remember that? It was a way to check and see if it is a normal distribution. So we are going to use the QQ plot to check normal. So we're going to turn the stat plot on. So once you have your data in, go to second y equals for stat plot. We're going to turn it on. And then pick the last chart here. That's our QQ plot. It's the one that compares each data point to the mean. Turn it on and then hit zoom stat number 9. In order to be considered normal, it would need to look like it's in a straight line pattern. Does that look like it's in a straight line pattern? So I could do like this. So I would say yes, it's normal. Did it work? Did y'all get it? Okay. Okay, the next thing, so that was part 1. Step 2 is use technology or a table A3 to find the critical values. So actually, we found the critical values here, and the critical value is 2.145. So done that. Number 2 was T alpha over 2 equals 2.145. I'm going to put from example 1. Okay, number 3 is our margin of error, so we are going to use that formula. E equals T alpha over 2 times standard deviation, the sample standard deviation over square root of n. So we plug in the values we know, 2.145 times S, our standard deviation, which was 2.9, over square root of 15. Okay, so 1 point, since we have the summary stats that we're using, we're going to go one more decimal place than that summary stats. So it'd be 1.61. Okay, and then number 4 is find our confidence interval. So if it's X bar plus minus 1.61, so we would take 30.9, which is our X bar, plus 1.61 and 30.9 minus 1.61 to find our upper and lower. $30.9 plus 1.61, 32.51, 30.9 minus 1.61, 29.29. So our confidence interval would be our lower. The next bar is, no, that should be mu, because we're talking about population mean. Because that's what we're finding the confidence interval of. So someone would be 95% confident that the mean, the population mean, would fall between these two values. I do want to show you all how to do it in the calculator now. We already have our data in there. So let's go to Stat, Calculate, Test, and go to t-interval. And let's use our data that we're given, because we've put that in L1, L2. What do we need to change that's not right here? 99. Yeah, what are we doing, 95? Okay, so 0.95. Calculate. So let's compare them. Oh, there we go. So that's if you're using the actual data. And then we can also do where we put in our summary stats. So t-interval, let's do our stats this time. We're given our mean is rounded to 30.9, and our sample standard deviation is 2.9. N is 15, and our level is 95. Calculate. 2.294 and 32.50. So if we were to round those to the hundredth place, then we'd actually get the same thing. Okay, let's look at example 3. A data set includes 109 body temperatures of healthy adult humans having a mean of 98.3 degrees Fahrenheit and a standard deviation of 0.54 degrees Fahrenheit. Construct a 99% confidence interval estimate of mean body temperature of a healthy human, of all healthy humans. What does the sample suggest about the use of 98.6 as the mean body temperature? So let's write down, what do we know? We know that our sample size is 109. We know that our sample mean, X bar, is 98.3. And our sample standard deviation, S, is 0.54. And we want to do a confidence level of 99%. So let's go ahead and use our calculator for this. We could do this using our table, but let's do it in our calculator. And then we still need to answer the question. So let's go to Stat, over to Test, t-interval, and let's plug in what we know, our mean, standard deviation, sample size, and our confidence level. Calculate. So it is 98.1. We need to go one more decimal place. So 1/6 is less than mu is less than 98 0.4. So to be 99% confident, or someone is 99% confident that the mean, the population mean, would fall between these two values. So what does this sample suggest about using 98.6? Everybody always uses that as the temperature. That's what everybody has. That's normal temperature. So what does this tell us about using this as our normal temperature to compare ourselves to? What's wrong with this?
It's a little higher than normal.
Yeah, it's higher. So 98.6 is higher than what the sample suggests. I know some people that are at like 97. 97 is like their normal range. And then other people who are a little bit above that. So I guess it kind of depends on your sample on this for sure. So 98.3 for 109. So of course, the more samples that you have, the closer it should get to the true mean. But right now, just using this sample size of 109, this is what we are 95% confident that the mean falls between. Okay, let's keep on going through our notes. We're almost done. So interpreting our confidence level. So that's the most important thing about this, not just finding it, but actually being able to interpret it and understand what the results mean. So for that example too, we are 95% confident that the interval from 92.2 Hg to 32.5 Hg actually contains the true mean of mu. This is a little caution. Confidence intervals can be used informally to compare different data sets, but the overlapping of confidence intervals should not be used for making any formal or final conclusions about the equality of the means. Okay, now we have a way of finding our sample size. So our goal is to find the sample size required to estimate the value of a population mean. So again, we have our notation. Here is our formula to find the sample size that we need in order to have a certain confidence level. Something important right here, it kind of got cut off, but you are going to round up to the next whole number. So even if it's like 5.1, you will round it up to 6. So that is kind of cut off, but it's there. All right, let's look at our example. How many STAT students must be randomly selected for IQ tests if we want 95% confidence that the sample mean is within 3 IQ points of the population mean? Okay, throughout the semester, we've talked about the IQ scores. What is the IQ score, the mean of IQ score? Do you remember? It's 100. 100 is your mean. And do you know what the standard deviation is? It's 15. And it's a normal distribution. So if they say, so we know that our confidence level is 95%. If they say we want the mean, the sample mean, to be within 3 IQ points of the population mean, what does that mean? What do we want the sample mean to be? What's within that 100? 3 points within that 100. You go above it 3 points, and you go below it 3 points. So that would be considered our margin of error, 3. So using this confidence level, well, let's go ahead and write down our formula so we know that we have everything. Our formula says our critical value that's our formula. And the reason we're using Z instead of T is because we know our our population standard deviation. So since we know that, we can use the Z. So a 95% confidence. So then what's alpha? 0.05. And then what's alpha over 2? Yeah. And so we need our other chart. So we need the critical value. So we can look down here and see what confidence level are we using? 95. So what's our critical value? 1.96. So our Z alpha over 2 is 1.96. Oh, there you go. All right, so we have everything we need. Now we're going to plug it into our formula. So 1.96 times our population standard deviation, 15, over our margin of error is 3 squared. So that equals 96.04 whenever you plug it in. So remember, we're finding the sample size required to be within 3 IQ points of the population mean. So what is our sample size going to actually be? Yeah. Because we round up 1. Okay, we're going to skip that and we are going to go over here. Choosing the appropriate distribution. So we'll use the T distribution whenever this population standard deviation is not known. And it's normally distributed or your sample size is greater than 30. We use our normal distribution Z. Whenever our population standard deviation is known, then we also have normal distribution and N is greater than 30. And then this last one, use bootstrapping method. We are not actually going to get to 7.4, so we don't have to worry about that. So this just tells you T distribution versus Z distribution. And that is it for today. Your assignment is on Pearson already.